All right, this is the exam 2 solution that I wanted to go through with you on video. I apologize that it's taken me so long to get around to that. But here we go. First problem is an energy problem. And we know it's an energy problem by virtue of the fact that it's asking for some speeds, and we're given some distances and some forces involved. If you look back up here to our little clue, energy for force, speed, distance problems. So this doesn't have any time involved, so you know that it's not a momentum problem. All right, so we have some beginning momentum or beginning energy at the bottom, 1/2 mv squared of both the truck and the boat. It has to climb this hill, and it uses positive work to climb the hill. The force of friction is going in this direction because that's what makes it climb up the hill. Many people got the force of friction going backwards, which slowed them down going up the hill. It didn't really make sense for that to happen, and got an erroneous answer. So the thing to recognize is force of friction pulls you up the hill, it's doing positive work, and then force of friction continues on doing positive work in this direction. So anyway, we have some 1/2 mv squared of the total system. I'm going to put my datum at the bottom, so I have no mgh at the bottom. I'm going to do positive work, which means that I have a mu mg cosine theta is the force of friction. Now the force of friction is only because applies to the truck because only the truck has the traction in this case. So that applies only to the truck. You don't use the mass of the truck here. Again, multiplying it by 30 meters, you get some 1/2 mv squared at the top and some mgh at the top. Solving that, you find that the speed at the top is 7.751. Because he actually has positive speed at the top, you know that he makes it. And that's an important step here, is to make sure that he gets to the top. We did some problems in class where he didn't actually get there. And so if he had gotten a negative answer here, then that would have been means he didn't have enough speed or enough traction or something to actually get up there. All right, then once you satisfy yourself that he gets to the top, then you move on and say, I'm going to go now from the top of the hill over to the end. And so again, yes, some 1/2 mv squared. I'm again doing positive work. Only the truck has traction. No cosine theta to worry about in this leg of the trip. Again, multiply the force of friction times that 30, and you find you end up with 1/2 or a speed of 14.12. All right, the next one is the momentum or the impact problem. And we did again one of these in class and homework where you bounced against a wall. The thing to recognize here is that the line lines up the mass centers, and then the plane is along the wall, and that the speed along the plane is the same, both approaching impact and after impact. So this guy has some speed by the virtue of the fact it's dropping, and the cosine of this middle of that angle right there is the plane speed, and then the cosine of this angle is the exiting plane speed. Several people messed up the angle, and let me just walk through that with you here. If this angle is 30 right here, then that angle is 30 right in there where my cursor is. If this angle here is 90, that means that angle right there has got to be 60. So again, this would be the cosine of 60 in the plane, and this would be the cosine of 45 in the plane exiting. Now, again, most people I think solved for the actual speed when it gets down there, and then found the actual speed after it left. And you can do that, but you don't actually have to. You can do this with ratios like I did in class, where you can you don't actually have to solve for the speed. So, but if you've done that, that's perfectly fine. But anyway, I set up a ratio for the plane, and then understanding that the line speeds are governed by the coefficient of restitution. So you have an approaching line speed and an exiting line speed with the coefficient of restitution. Plugging that in, you get 0.577. Okay, this one, the understanding here is that everything is the same for all three scenarios. In all three cases, the student has the same 1/2 mv squared, whether you fire it at an angle, straight out, or straight up. The 1/2 mv squared is going to be the same, and they also start with the same mgh. So this is a conservation of energy problem. Mgh of 1/2 mv squared is going to be the same for all three scenarios. Now again, bouncing off the wall says that that you might have some energy loss, except that what we said is that there is no energy loss if the coefficient of restitution is 1. All right, in this relative problem here, this momentum problem. This is a skateboard problem, which we did more than one of. But what we're looking for is to understand that the conservation of momentum applies. And it says that at the beginning of the problem, everybody stopped, and the momentum of the system is 0. After they start moving, then you have they're moving, but the system momentum is still 0. And so I say that 0 is equal to MAVA plus MBVB plus MCVC, and then I get one equation with 3 unknowns, which doesn't help me very much until I understand that the relatives equations also apply. So if I solve these for VA and VB, plug them into here, then I can solve for VC in that equation, and then plug in those VC into either one into those equations, and I can solve for the other two. Okay. All right, now this is the power problem. Power, we understand that we always start with a free body diagram, and we understand what's going on. And that is the force of the wheels is actually moving this car and accelerating it to the right. The force of the wheels acts through the friction. This isn't a friction problem yet, but it acts in this way. It's resisted by the force due to the aerodynamic drag. In this case, we don't have an mg sine theta to worry about because we're not having any hill to climb, or there's no other friction involved. So we set the force equation. Some of the forces is mass times acceleration. And I just said the force of the wheels is pushing it forward, force of drag is pulling it back, and that's equal to my mass times acceleration. Solving that for the force of the wheels, and I get this as a function of velocity. Then the power is this equation. Power at the engine times the efficiency is power at the wheels. We recognize power at the wheels is the force at the wheels times the velocity. Plug in all those in there, and you can solve that for velocity is equal to 86. Now here the understanding, or once you get this equation, then you can see that if you multiply this v into here, you got a cubic, and then that would be just v times that. So you had to use either a solver or have to graph it or something like that in order to be able to make some sense of that one. And that was part of what I was looking for, is can you solve a more difficult equation like that? All right, now this one was a momentum problem, an impulse momentum problem. We did a couple of these, we did about 4 or 5 of these where we're trying to find the maximum or minimum speed in a particular scenario. And we said that where the acceleration is equal to 0, there's where the maximum speed generally occurs. So we can start with some of the forces in the x is mass times acceleration in the x. So I have this tension, which is the pulling force, which is 50 minus 5t. And I have pulling back, I have the friction force, and setting that equal to 0, and I can solve that for a time at which the acceleration is equal to 0. And when the acceleration is equal to 0, again, that's where we understand that that's where the max speed occurs. Now, the momentum equation says that I have some beginning momentum, I have some impulse due to the force in the tension in the string, and I have some impulse due to the friction that I have to work it out, and then I have some ending momentum, some ending mv. So I'll just plug those in. I have some beginning momentum. I have to integrate the pulling force because it's a function of time. I don't actually have to integrate the force of friction. I can just multiply it by the time, and I can find my ending momentum or ending mv. Integrating that, and then I get this equation, which is velocity as a function of time. Plug in that time in there, and then I can solve that for v2. The other way to think about this is you could have come to this point and said there is a velocity versus time equation, and I could have taken this equation, taken the derivative and set it equal to 0 and solved for time, or I could have graphed this and then found that the peak speed occurs at t equals 2.6. All right, this energy problem or energy understanding suggests that it has some beginning energy, 1/2 mgh, and has some ending energy, 1/2 mv squared. Which one will get there the soonest? Well, clearly if it's dropping at a steeper angle, then it's going to get there faster. Whereas this if it had a very slight, shallow angle, it may not have been, it may have been easier to see, but the angle rules here, and it says that this one gets there soonest because it has a much steeper angle to go down. The speed is going to be the same because they both have mgh and 1/2 mv squared, and there's no friction slowing it down. But the energy is determined by how much energy it has at the bottom, which is 1/2 mv squared, and clearly that one has more mass, so that has more energy. All right, the last two problems here were 5-point problems. I gave partial credit on all the rest of the problems. I did not give very much partial credit here. I was looking for, do you get it? These are quite difficult problems, and I was hoping that these would challenge some of you. And so unless you made some substantial sense in your solution, I generally didn't give very much partial credit. However, this problem was in the video where we had a compressed spring. It pushes B out that way and pushes C this way. And so if you understood that, that is an energy problem. And so we start with energy, and we say that conservation of energy applies because during the spring expansion, there's no losses. We're going to ignore the friction during the spring expansion. So I can say that I have some beginning energy of 1/2 ks squared. And when it pushes those things apart, I have the 1/2 mv squared of the box and 1/2 mv squared of the cart. And so I have one equation with two unknowns. It's a valid equation, but I have to find something to do with that. All right, so I need another equation to move forward, but I also recognize that the conservation of momentum applies. That at the beginning of the problem, with the spring compressed, the momentum of the system is 0. After the spring expands, the momentum of the system is still 0. So in other words, mv of the box is going to be equal to mv of the cart. And so I plug that in, and I have two equations, two unknowns, and I can solve that for the velocity of the cart going backwards at 0.577 meters per second. The next thing to understand is after they stop moving relative to each other, what's the final speed? Well, stopping moving relative to each other means that there is friction slowing this thing down. This box is moving that way, cart's moving that way, and there is friction, and at some point in time they're going to stop. And so again, momentum tells us that beginning momentum is equal to 0. During the time they're traveling, momentum is equal to 0. After they stop moving relative to each other, momentum is equal to 0. So the final speed of the box and the cart are both 0. Now, how far does the cart actually move? That's where we have to use an energy approach. And we say that as the box moves that way, the force of friction slowing it down is going to be transferred equal opposite to the cart. The cart moves to your left, and the force of friction is slowing it down. Those forces of friction are the same force of friction, have to transfer equal opposite from the box to the cart. And if I do that, I can solve for the distance that the cart actually moves. All right, in the last 5-point problem, again, I didn't give much partial credit here. This was a homework problem, virtually identical to a homework problem that if you'd remembered that, you'd have been in good shape. But it has an NT component and it has an energy component. The NT component, NTB, helps us understand the tension. And the energy component helps us understand the 1/2 mv squared at the top. And by the time it loses tension, it has, tension goes to 0. Then it has gained some mgh, but it still has some 1/2 mv squared at the top. And if we remember, we did this demo in class where we had some speed at the bottom, and then it goes doo, and then it keeps coming, then it falls back like that. So anyway, those are the ways to look at this. Again, it was a homework problem, and I was hoping that you'd be able to walk through the solution on that. All right, where's my cursor? Oh, I guess I can't get here. I can pull this box down here. Come on. There we go. Now you can get to the rest of the problem. 123.81 was the answer.